This is a simulation of a walking hexapod robot that's controlled by a relatively simple neural network based on the walking circuitry of the cockroach. Before I show the video of it in action, I'd like to explain a little bit about what you'll be seeing so you'll have some idea of what's happening in the video. This model was built in the neuromechanical simulator called AnimatLab. This application allows you to build accurate models of the bodies of organisms or robots, and then build biologically realistic neural networks to control their behavior in a physically realistic environment. This is a hexapod body that I built in SketchUp using photos of the real parts. All of the models in this simulation either downloaded from SketchUp's 3D warehouse or built directly into SketchUp. The hexapod robot has 6 limbs with 3 degrees of freedom in each. The first joint moves back and forward, the second joint moves up and down, and the third joint moves in and out. However, for this simulation, the third joint is not used. Each joint is driven by a small servo motor. The maximum forces and velocities that the real servo motor can apply were used to model the ones for the simulation. The robot also has several sensors. It has a basic on-off pressure sensor on the bottom of its foot that tells it when the foot is on the ground. It can also detect the angle of each joint in its leg. And on top, it has 4 pan-tilt mechanisms with sonic rangefinders attached, 2 on the front and 2 on the back. Currently, only the ones in the front are functional, and they're only used in a simple binary fashion. If there's something within 45 centimeters of their beam, then they signal this to the robot. It uses this during navigation to stay away from the walls. The simulated robot also has a sense of smell. It uses a simple odor tracking mechanism to interact with its environment. It has odor sensors located in the front of it and underneath it. There are also small toy blocks scattered in the 2 rooms of the house that each emit an odor. There's also a toy box that emits an odor. The robot uses the odors to find the toy blocks and move them back to the toy box in order to clean up the rooms. To do this, it has a small scoop underneath it on the bottom that extends to catch a block and then take it back to the toy box and leave it. Finally, there's also a battery charger mat located here in the kitchen. It also emits an odor. As the robot moves around, it uses energy. When its battery gets low, it must find the charger and move over top of the mat and stay there in order to recharge its batteries. If the batteries go to 0, then it dies and the simulation is over. This odor tracking is not very realistic for real robots. One way something like this could be implemented would be to use RF tracking tags. However, I really see this as just a stopgap to explore some of the more complex behaviors. In a future version, I'd like to begin adding some simple visual processing capability to this system, and that will be much more realistic and useful for a real robot. That's the basics of the body of the robot. I'd also like to explain just a little bit about the neural network that controls its behavior. This is the neural network editor. It allows you to build a hierarchical network built of subsystems. In this top one, we can see that each leg has its own identical network controlling it. Each leg has a central pattern generator that acts as a type of oscillator to drive the rhythmic motion of the leg. Sensory feedback then refines those movements. For example, when a leg becomes loaded by contacting the ground, then the downward motion is stopped and it maintains that posture. Or when the leg moves all the way backwards, it signals to raise the leg and move it forward in a new step. Each leg is coordinated using reciprocal inhibition between the pattern generators in each of the legs. This allows it to automatically produce a tripod gait that keeps the robot steady while allowing it to move forwards or backwards. It also makes it very robust to changes. We can easily slow the robot down or speed it up. The network simply adapts to the new controls without any extra programming or design on our part. In this version of the robot, turning is done in 2 different ways. The first is more subtle. We simply slow down the walking on one side versus the other. This leads to a slow turn in one direction. The other is a bit more dramatic. We can set one side to go backwards and the other forwards. This lets the robot turn like a tank and rotate in place. There are also subsystems to control the antenna, and the navigation to the toys in the toy box. Different subsystems can override others. For example, if the battery is low, it overrides the behaviors of finding toys or going back to the toy box. Overall, the neural network that controls the behavior of the robot only has 695 neurons and 812 synapses. This is nothing compared to even the simplest of insects. But as you'll see, this is still able to produce some very complex, autonomous behaviors. So let's go ahead and take a look at the robot in action. So for the sake of time, let's go ahead and start this simulation over again, and I'll replay it back at 4 times normal speed so we can kind of see it in a more long-term setting. As you can see, while this robot performs some very lifelike autonomous behavior, it's far from perfect. In fact, its battery will die here in just a little bit because it gets hung up on the wall while trying to get back to the charger. One thing to keep in mind, though, is that nowhere was any explicit knowledge of its environment programmed into the robot. It can only detect its environment using the few sensors that I discussed earlier in the video. Its ability to navigate through a door or around tables just naturally emerges from the interactions between the neural network and its environment, just like in a real animal. There are a number of improvements that can be made to this robot to make it better. One thing will be to add some way for the robot to grab the blocks instead of just scooping them. Just scooping them has a tendency to push them into the wall, and this causes problems. We can also make it more intelligent when it gets near a wall. If there's a block near the wall, we could use the actual range information on how close it is to the wall, and slow the robot down so it can get close to the block without hitting the wall. Another improvement would be to add contact sensors on the legs to let it know if it is actually touching the wall. For example, it has a tendency to get stuff between its legs and get caught. If we had sensors to detect this, we could use the third joint to let the robot push out like a crab walking sideways in order to escape. Finally, as I mentioned earlier, real visual processing will make this robot much more useful. I currently have plans to upgrade the neural processing code to run in OpenCL so it can be processed in parallel on a GPU. This will make it possible to begin adding the large number of neurons that are necessary to do the visual processing. I then plan to get the AnimatLab code to run on a new Parallella board. This is a small GPU-type mini-computer board that can be used to control robots. This will make it possible to run the same OpenCL neural networks on the real robot that are run in the simulated models. Please go to www.animatlab.com to find out more, or to download the simulation, or to download the software itself. Thank you.